let's start. Okay. So last semester I talked about this, but let me just remind you. What is this? Let's consider the following matrix. 1, 1, 1, and I would say x1, x1 squared, x1 to the power n, and here I have xn minus 1, xn minus 1 squared, and xn minus 1 to power n. So this is an n by n matrix, right? N by n matrix. That x1 up to xn minus 1 are just field elements. Okay. So here you have a real number, and then its powers, and then you have x2, x2 squared, and so on, xn minus 1, and so on. Okay. The fact is the following. Determinant of this matrix is just the product of these numbers, xi minus xj, are larger than j. Let's do one example. For example, n equals 2k. So A is this matrix. 1, 1, x1, and then x1 squared. Then what is determinant of A? Determinant of A is just evet, yanlış yazdım değil mi? Evet. Şimdi yanlış yazdım. Pardon. I'm sorry. 1, 1, 1, x1, x2, xn, x1 to the power n minus 1, x2 to the power n minus 1, xn to the power n minus 1. Yes, so, okay. So 1, 1, x1, x2. So what is the determinant? It is just x2 minus x1. Okay. N equals 2. So it is just 1, 1, 1, x1, x2, x3, x1 squared, x2 squared, x3 squared. And determinant of this is just x2 minus x1, x3 minus x1, and x3 minus x2. You can check this. I mean, it's not difficult. And this. How do you prove this? So, proof of general case. In the book, there is a proof using answer notation, exterior powers, exterior products, but let me give you a simple proof. The idea is the following. So let me rewrite this matrix again. X1, x2, xn, and then x1 squared and so on, x1 to the power n minus 1, x2 to the power n minus 1, xn to the power n minus 1. Okay, now what is the determinant of this? Now, if A was this, let's say ARJ, okay, then what is the determinant? Determinant of ARJ is like something like it's a summation. The summation over all permutations. You have sign of the permutation, and then you have this A, let's say 1 sigma 1 A and sigma n. And this corresponds to the following. So if this is, let's say, like this, A11, A12, A1n, A21, A22, A2n, and so on, and 1, and 2, and n. What is this expression? It is the sum of all kinds of products. What kind of products? From each row, you pick up an element. For example, you can pick this one, but once you pick an element, from the second row, you pick an element which is not in the same column. So you have to choose something from other columns. For example, you may choose this one and so on. So you get the product of diagonal entries. Or you can do something like this. You may choose this one, and then you can choose this one, and then so on. So from each row and each column, you pick one element, but in each product, all the elements should lie in different rows and different columns. So what will be the determinant of this one then? Now, each of these products, so there are n terms, and each of them will contain exactly one element from each row. So it will contain one of these ones, so it will be 1, and then it will contain one of the xi's. It will contain one of the xi squares and so on. So what will be the degree of this gadget? Degree. Well, degree of this one is 0 because it's a constant. And then you pick one element from this, it has degree 1, right? Xi, x1 or x2 or x3. And then you have a second degree term, xi squared, and then xi cubed, and so on. So as a polynomial, the degree will be the following: degree 0, degree 1, degree 2, degree 3, degree and minus 1. So the degree of this guy will be this 0 plus 1 plus and so on up to n minus 1, right? Because from each row you pick up exactly one element, and the degree of that is either 0 or 1 or 2 or n minus 1. So degree of each of these polynomials is the sum of all these numbers. And what is this? This is the sum of integers from 1 up to n minus 1. So it is n times n minus 1 over 2. Therefore, this determinant of n is a polynomial. In the variables x1 up to xn minus 1, no, xn in n variables of degree n times n minus 1 over 2. Okay. All right. What else do we know? Well, from the properties of determinants, we know the following. If two rows or two columns of a matrix are the same, then the determinant is identically 0. For example, if x1 and x2 are the same, then of course these two rows will be the same. Therefore, the determinant should be 0. So, in this polynomial, if I write x1 is equal to x2, so whenever I have x2, if I write x1, that thing should be 0. This means what? So, in the polynomial, right? So let's call that polynomial f x1 up to xn. So this is the determinant of a. Okay, it's a polynomial of degree n times n minus 1 over 2. I know that if I write, for example, this, then this is identically 0. If these two are the same, it is 0. Actually, it is true for any two variables. If two variables are the same, it is 0. This means what? This means the following. This polynomial has the factor x2 minus x1 in it. So this implies actually x2 minus x1 divides this polynomial. Tamam mı? Bu onu söylüyor. Okay. Bunu şöyle görebilirsiniz aslında. This is something we know from high school, right? If you have a polynomial, f of x, one variable, and suppose f of a is equal to 0. This means what? X minus a divides f of x, right? F of x has this thing as a factor. That's just the generalization of that fact. How can I relate this to this one? Well, you may relate it this way. Take this polynomial f1, x2, xn, and consider all the variables here as constant. Okay, so let me just consider x2, xn as constants, and consider this as a polynomial of a single variable x1. Yani bunları parametre gibi görün, bunları sayı olarak görün. Tek değişkeni şöyle görün, x1 olarak. O zaman ben bunu şöyle yazabilirim. Bu p of x1. And what we know is that suppose this is, a to an. And I know that if I write here a2, I get 0 because putting a2 here, I will have a2, and so the two rows, two columns are the same, therefore this is 0. But this means what? This means x1 minus a2 divides this polynomial, gx1. Okay, but what does this mean? And gx1 is nothing but this polynomial, and this guy just divides it. So this means x1 minus x2 actually divides x1 up to xn. Okay. So this way we see that this guy divides this polynomial. But then what do we know? Well, this is not true just for x1 and x2. It is true for all the actually variables. Similarly, xi minus xj divides f1 up to fn for any I and j different. Let me just choose this way for I larger than j. But, well, this means what? X1 minus x2 divides this polynomial. X1 minus x3 divides this polynomial. no, x3 minus x1, x3 minus x2, x4 minus x3, x4 minus x2, and so on. All those gadgets divide this polynomial, but for different INJ, these are irreducible elements. One of them doesn't divide the other one. Therefore, all of these gadgets for I larger than j are factors of this. Okay, so this implies this gadget xi minus xj for I different than j, all of them divides this polynomial. Yani şöyle diyorum. x2 eksi x1 bu polinomu bölüyor. x3 çarpı x1 de bu polinomu bölüyor. Ama bu ikisi birbirini bölmediği için bu ikisinin çarpımı da bunu bölecek. Bunlar hani irreducible elementler. O yüzden x2 eksi x1, x3 eksi x1 bu da bunu. Dolayısıyla da bütün bu çarpımlar bunu bölüyor. But what are the degrees here? This is degree n times n minus 1 over 2. What is the degree of this one? I is larger than 1. J can be at least 1. And this is at most n. How many pairs you may choose? There are and choose 2 pairs, right? And choose 2. But this is just n minus 1 over 2. So they have the same degree. Okay? This polynomial divides this polynomial and they have the same degree. It means that one of them is a multiple of the other one. Değil mi? İkisi de aynı derecede ve biri diğerini bölüyorsa biri diğerini katı. So this implies that fx1 up to xn is just some lambda times this gadget. And then you just compute this gadget. How? I mean, you can just look at, this simple cases, the case n equals 2 and 3, and then you determine that this number is nothing but 1. Okay? Burada biraz el kol sallıyorsunuz ama dert değil. Kitapta bir başka ispat daha var. Yani ona da bakabilirsiniz. Ama bence bu ispat gayet iyi bir ispat. Peki. Şimdi bunu nasıl kullanabiliriz? Bunu two applications of this determinant. One application is the following. Let me write that as a okay. So two applications. One of them is this one, linear independence of eigenvectors. Proposition. Suppose that the vectors E1 up to En are non-zero. And are eigenvectors vectors of an operator. Actually, we defined eigenvectors to be non-zero vectors. So this part of the assumption is kind of unnecessary. When you say eigenvector, it is already non-zero. Nevertheless, operator A with all different eigenvalues, lambda 1 up to lambda n. Then the set is E1 up to n is linearly independent. Okay. In particular, you see, if this is linearly independent, of course, the number of vectors cannot be larger than the dimension of the vector space. So n should be larger than the dimension of the vector space, but that n is also number of this distinct eigenvalues. Therefore, for an operator, the number of distinct eigenvalues cannot be larger than the dimension of the vector space. Okay, there is a corollary. The number of distinct eigenvalues of an operator has from E to D is cannot be larger, is less than or equal to less than or equal to dimension of D. Çünkü bu linearly independent, since this is linearly independent, dimension of this, the number of vectors here, which is n, less than the dimension of the vector space, but this dimension is the same as the number of distinct eigenvectors here. Therefore, we have this corollary. Proof of the proposition. All right. So we claim that this set is linearly independent. So to show that a set is linearly independent, you just take an arbitrary linear combination, set it equal to 0, and then show that all the coefficients of the vectors are necessarily 0. So let C1, Cn is in K, so that C1, E1, Cn, En is equal to 0. Okay. Ne yapmamız lazım? We must show all these Ci's are equal to 0, right? That's what we need to show. How can we show this? Well, we can do the following. Take this equation and apply a head to both sides. Okay? Apply a head to both sides to get a head of C1 E1 Cn is equal to a head of 0. Since it's a linear map, this is 0. What about this one? Well, this is just C1 times a head E1, Cn times a head En, and that is 0. Well, what is this? This is an eigenvector with eigenvalue lambda 1. So this is just C1 times lambda 1 E1. The next one is C1 times, no, C2 times lambda 2 times E2 up to n term Cn times lambda n times En. Tamam. Because En is an eigenvector with eigenvalue lambda n. So the meaning of this is just E head of Ei is just lambda I times E for each I. All right, so we have this. I did this once, I can do it again. So let's hit this guy with a head one more time. So a head of C1 lambda 1 E1, Cn lambda n En, a head of 0, which is just 0. And if you hit this guy with a head again, so I would have C1 lambda 1, a head E1, Cn lambda n, a head En equals 0. But what is this? This is also lambda 1 times E1. I have already one lambda 1 here, so I will have C1 lambda 1 squared E1. Cn lambda n squared En equals 0. And I can repeat this as many times as I want. So what we will get equations like this. I had this equation, and then I have this equation, and then we have this equation. So each time I have this powers of lambda i's will increase. Here I have lambda 1 to the power 0, right? Just 1. Here lambda 1 to the power 1, lambda 1 squared. If I repeat this, I will get lambda 1 cubed, 4 power, and so on. So this is what we are going to get. Okay. So we get the following system. Of equations. Bir tanesi C1 E1 Cn En equals 0. C1 lambda 1 E1 Cn lambda n En equals 0. C1 lambda 1 squared E1 Cn lambda n squared E1 equals 0. And this is true for all integers. C1 lambda 1 to the power k E1, Cn lambda n to the power k En equals 0 for all k. Okay. Let's just stop at the level. So let's go from this corresponds to k equals 0, k equals 1, 2, 3, up to n minus 1. So that I have n equations, and I have n unknowns. These are my unknowns. C1 up to Cn. So I have like n equations and n unknowns. Okay, so let me write it this way. Şöyle. Şimdi burada yani aslında tam bir şey doğru bir yazı değil ama şöyle yazdığını düşünün. Bak. Şöyle. Değişken vektörü sadece C1 değildir. C1, E1 gibi yapıyor. C2, E2, Cn, En. Şurada 0, 0, 0. And here I have what? 1, 1, 1. And then lambda 1, lambda 2, lambda n, lambda 1 squared, lambda 2 squared, lambda n squared, up to lambda 1 to the power n minus 1, lambda 2 to the power n minus 1, lambda n to the power n minus 1. This writing is actually a little problematic. Why is that? Because these are numbers. These are not numbers. These are actually vectors. But you know, still I can consider this equation. And how can we solve this? Well, this is a homogeneous equation, and this coefficient matrix has determinant. What is the determinant of this? Determinant is just lambda I minus lambda j, product of these, that I is larger than j. But by assumption, I know that these are different eigenvalues. So all these vectors, numbers are non-zero. They are never equal to each other. So this is a product of bunch of non-zero scalars. Therefore, this product is not zero. Therefore, this matrix is invertible. If it is invertible, I can just multiply this equation by the inverse of this and obtain zero. Therefore, this column should be zero. So this is what we are going to obtain. Since the coefficient matrix is invertible, because it has non-zero determinant, the vector, each vector, this vector, C1, E1, En, En, this vector should be 0, 0, 0. But this means what? This means Pi times Pi is 0, for Pi from 1 up to n. And we know that by assumption, this vectors are eigenvectors. They are non-zero, right? They are non-zero vectors. So since these are non-zero, this is not a zero vector. This implies Pi is zero. for all I. Since PR is not 0. So this finishes the proof, right? That was what we were supposed to show. C1, C2, Cn are all 0. That was our aim. We needed to show that these coefficients are 0, and that's what we showed. Okay. Bir başka şeyde uygulamak. Another application is polynomial interpolation. What is this? Okay, proposition is this. If the numbers x1 up to xn are all different, in whatever your field is, okay, not necessarily real numbers in any field, and the numbers y1, yn if they are arbitrary, so these numbers doesn't have to be distinct, okay? Xi's are distinct numbers, but these are arbitrary numbers. You may choose, for example, all of them to be 0, okay? Anything you like. Then there exists a unique polynomial of degree px of degree at most n minus 1. So that the value of this polynomial at xi is equal to yi for all I. Right there, 1 up to n. Yani şunu söylüyor. Mesela if you choose k equals, let's say, r or q, okay, then we may picture this in Cartesian coordinates. So what it tells us the following: if you choose distinct numbers like this, x1, x2, x3, let's say x n minus 1, xn, just arbitrary distinct numbers, and choose arbitrary y values. Y1 here, this is y2, this is y3, and so on. Let's say yn. Okay, and then what you get here, this point x1 y1 is this, x2 y2 is this one, x3 y3 is this one, and so on. X and yn is this one. Okay, what it tells us that there exists a unique polynomial whose graph passes through all these points. This point, this point, this point, and this point. So we have a polynomial function, something like this. Right? It satisfies this condition for each I. So it passes through the point xi, comma yi. The point here is that the degree is of this polynomial is n-1, at most n-1, if you have n many points. So that's the statement, and how this is constructed. Şöyle. Okay. Now consider a polynomial of degree n-1. Let's say Px P0 plus P1 x P2 x squared P n-1 x to the power n-1. And then let's try to choose. Let's try to choose these coefficients P0, P1, Pn-1, this coefficients in the field K, so that Pxi is equal to yi for all I 1 up to n. Yani şöyle diyoruz, madem ben böyle bir polinom istiyorum, bir tane böyle polinom yazalım, katsayılarını bulmak istiyoruz. Öyle ki bu polinom şu denklemleri sağlayacak. N tane denklem her ay için. Yazarsanız bunu ne çıkacak? So let's just write down what this means. This is just P0 plus P1 times xi, P2 times xi squared, Pn-1 times xi, n-1 is equal to yi for I equals 1, 2, and up to n. So I have n many equations. One of them is for x1, and then for x2, x3, x4, and so on. If you write all these equations in a matrix form, this is what we are going to get. For I equals 1, what are the coefficients? So Pi's are, these are the unknowns. So that's my unknown column, P0, P1, up to Pn-1. That's equal to, this column is just y1, y1, y2, yn. And what is the coefficient matrix? For I equals 1, what are the coefficients? 1 times P0, x1 times P1, x1 squared times P2, and so on. So the coefficients are 1, x1, x1 squared, x 1 to the power n minus 1. For the second equation, I equals 2, I will have x2 squared, and so on. So it is just 1, x2 squared, x2 to the power n minus 1, and so on. And then xn squared, and xn to the power n minus 1. Again, the same matrix, actually not exactly the same, it is just its transpose, right? Hangisini? Hangi özelliğini kullanmak mı?
Şey yaptık ya. Çarpım şeklinde bulacağını söyledik.
Yok. Yakısını göremedim ama. Ya ben görmüyor da olabilirim. Sen düşün, sonra konuşalım. Okay, now what is this matrix? This is Vandermonde matrix, but actually it's transpose, right? If you take transpose, you get that matrix. But determinant doesn't change. What is the determinant of this one? Determinant of this matrix is again xi minus xj, I greater than j, and by assumption, all these xi's are different. They are distinct elements. So none of these terms is zero. Therefore, this product is not zero. Therefore, this is invertible. Hence, by just multiplying this equation with the inverse of this matrix, I can solve this, right? So this equation can be solved. This equation has a unique solution. Okay. Why do we say that degree is at most n minus 1? Right? It seems that degree is like n minus 1. But degree is at most n minus 1 because of the following. Maybe this coefficient might be right 0. In the solution, this might be 0. The one above this one might be 0. So maybe, you know, this coefficient is 0, this one is 0, and so on. In that case, of course, the degree of the polynomial will be less than n minus 1. Okay, that's why in the statement we say that unique polynomial of degree at most n minus 1, because it is not clear that why this coefficient is not 0. Maybe it is 0. Remember? But this tells me that there is a unique solution. Actually, we can write down the solution at least in the you know, small cases where n equals 2 or 3. Let me just write that down. This is something used in practice, I guess, in numerical analysis. And, of course, probably there are better approximation methods, but this is one of them. So let's do one example. Ya da bir dahaki ders yapalım. Tam buçuk olmuş. Okay, let's stop. I'll continue in the second hour.